Welcome to Feynman's Technique. Today we are going to do three similar integrals. They are these three integrals. They are all evaluated from 0 to 1, and they are both the functions f of x, three functions over x, and these three functions, they are all inverse functions. So I'm going to do the first one, and three of these integral, only one of them is a divergent integral. So now we are going to do the first integral first. Integral of inverse sine x over x dx from 0 to 1. And this integral actually, these three integrals actually are non-elementary integrals. So, but if these are definite integral, it actually gives you the result, beautiful result. So this one, I'm going to take the integration by part. Use the DI method. I'm going to differentiate inverse sine x and integrate 1 over x. Integrate 1 over x, you get ln x. Because this integral is evaluating from 0 to 1, so we can just ignore the absolute value of this ln x. And then this differentiate inverse sine x, you are going to get 1 over square root of 1 minus x squared. So you are going to get the inverse sine x times ln x from 0 to 1. Evaluating from 0 to 1 minus the integral from 0 to 1 of ln x over square root of 1 minus x squared dx. So we are going to deal with this limit. Inverse sine 1 is pi over 2 times ln 1, which is 0. Pi over 2 times 0, which is just 0. And then we are going to minus the limit. When you plus 0 into it, 0. ln 0, it should be 0 plus here, because the integral is evaluating from 0 to 1. Not evaluating, it's going from 0 to 1. Which is, this limit tends to be negative infinity. 0 times another negative side, 0 times infinity itself is just an indeterminate form. So we have to use our L'Hopital's rule to do this. X approaches to limit as x approaches to 0 plus, and then inverse sine x times ln x. Because you can get 0 times negative infinity. 0 times infinity itself is just an indeterminate form, so we have to do more work. What functions should we put down the denominator? To write it as 1 over something. I think it's ln x or inverse sine x. I'm not sure whether I can do this because these two functions are kind of complicated. Let me try to put our inverse x on our denominator. Inverse x, 1 over inverse x, like that. So we can do our L'Hopital's rule. Differentiate the top and then differentiate the bottom. So differentiate the top. Don't forget to write down the limit at x approaches to 0 plus. And then the top, you are going to get 1 over x. And the bottom, first you are going to square this function. Because it's the inverse function, we should write the square like that. Parentheses and then square. And then whenever you are going to do the derivative of 1 over functions, you should get a negative sign here. This square, function square, and then differentiate inverse x, which you are going to get 1 over square root of 1 minus x squared. So we can put the negative sign outside the integral. So you are going to get something like inverse sine x square on the top. And then you are going to get this over this, you're going to get 1 over x, and then because this is inverse sine x square over this. So when you ever 1 over x divided by that, which is just switch the sign, which is inverse sine x on the bottom, and then square root of 1 minus x squared on the top. Am I right, guys? The line should be written longer. So this is my mistake. So you can get 1 minus x squared x times inverse sine x squared here. So you are going to get something 0 times 0, right? 0 times 0. And at the top you're going to get 1 over 0, which is negative infinity. But I'm not going to do. I may make some mistakes here because this limit is kind of hard to evaluate. So I'm going to give you this limit is just equal to 0, and then we need to move quicker. This integral, we are going to, because you see a 1 minus x squared here, we are going to let x is equal to sine theta, which this is equal to cosine theta d theta, when our theta is equal to inverse sine x. So to the inverse 0 is equal to 0, inverse sine 1, it should be inverse sine 0 and inverse sine 1. Inverse sine 1, you are going to get pi over 2, and then ln x, which is equal to sine theta, and then you get cosine theta divided by 1 minus sine square theta d theta here. Since 1 minus sine square theta is equal to cosine square theta, take a square root, you get cosine theta here. So this and this cancel out, and you're going to get the integral from 0 to pi over 2 of ln sine theta. And this integral, you get a famous result, which a lot of YouTubers talk about. This integral, a really famous integral from 0 to pi over 2 ln sine theta. You are going to get negative pi over 2 ln 2. So negative beyond positive, so over you can get this integral is pi over 2 ln 2. So this is our first integral, and our second integral is going to be a divergent integral. Integral of inverse cos x over x. So remember we have a formula which is inverse sine x plus inverse cosine x is equal to pi over 2, which we can written inverse cos x as our pi over 2 minus inverse sine x. So you are going to get pi over 2 on the top minus inverse sine x over x dx. So you can get pi over 2 split to 2 different integrals minus this 8. This integral we've already done that, which is equal to negative pi over 2. So this integral, it does converges, while this one is not, because when you integrate this 1 over x, you are going to get ln x. Forget the absolute value, actually forget don't need to use the absolute value here, because the integral is evaluated from 0 to 1. So ln 0, you can get ln 0 here, which is an indeterminate form, not indeterminate form, but undefined. Overall, you are going to get this integral is divergent. Divergent integral minus convergent integral, pretty much this integral is just divergent. So number 3, we are going to get our final integral, inverse sine tangent x over x. So here's the deal, we are going to use our summation here. Inverse tangent x, the summation of this, remember this, the summation at n is equal to 0 to infinity, and then negative 1 power of n, x power of 2n plus 1 over 2n plus 1. And then when you divide by x, which tells you this one, you are going to get x power of 2n over 2n plus 1. And then, yeah, just divided by x here. So we can change this into our summation form. Inverse negative 1 power of n, x power of 2n over 2n plus 1 dx. After you switch the order between the integral sign and the summation sign, the integral is gonna be convergence. So we can switch it. You get negative 1 power of n over 2n plus 1. And then the integral from 0 to 1 x power of 2n dx. So this integral, how can we do this though? N1 to the power divided by a new power, which is 1 over 2n plus 1 times x power of 2n plus 1 from 0 to 1. So overall, you're going to get the summation as n is equal to 0 to infinity, which is negative 1 power of n over 2n plus 1 square. Yeah. So overall, you get this summation. This summation, which is equal to our Catalan's constant. Which is equal to our Catalan's constant. Which is equal to g. We can write this as g. And some people write this Catalan's constant as c as well, because c stands for the Catalans, right? But I may use g here because it's way easier to identify the constant which come from the indefinite integrals. For example, integrate x dx from 0 to integrate x dx, just indefinite integral. Integrate this, you probably get 1 over 2 x squared plus c. I just don't want to mess up with this normal constant c and this Catalan constant. Yeah. So I use g here. And another easier ways to evaluate this integral is way easier, because the integral of inverse tangent x over x, which gives you the inverse tangent integral, which is called ti to x. You can check the definition of this, the inverse tangent integral ti to x here. So ti to 1, which gives you the Catalan's constant, and then minus ti to 0, which is 0. So yeah, it's just the result, g. Yeah, I hope you guys enjoyed this video. So goodbye. These 3 similar integrals.